Okay, so this video is intended to recap sinusoidal steady-state analysis, and so I broke that up into an overview of sinusoids and then 4 parts describing how we get to being able to do sinusoidal steady-state analysis, and that's where we are analyzing a circuit in the frequency domain using the phasor form of the voltages and currents and the impedances of our passive elements. So this video is going to overview the basic method required to do that and illustrate a couple of examples. So the first thing that we're going to do is transform a circuit from a time domain equivalent into a frequency domain equivalent of a circuit. So we do so by first converting the voltage and current sources to phasors. So we're going to use the phasor form of voltage and current sources. So for example, if we want to convert the phasor or the time domain expression A cosine omega t plus theta, in the frequency domain, the magnitude or the amplitude of that is A with a phase angle of theta. We only need those two parameters, magnitude and angle. If we want to convert the expression, the time domain expression B sine omega t, that in the frequency domain is B at an angle of -90. The reason it's -90 is because we convert all sines to cosine form first, and that's a -90-degree phase shift. Okay, second, we're going to find the impedances of our passive elements. And just as a reminder, the 3 passive elements we've talked about thus far are resistors, inductors, and capacitors. And in the frequency domain, the impedance, Z, of those passives are R, J omega L, and 1 over J omega C, respectively. So resistors are the only ones that are independent of frequency. Both the inductor and the capacitor have a frequency-dependent component. So a couple ways to remember this. First, recall that capacitors are open-circuited in DC conditions. DC conditions is like a frequency of 0. So if we take the limit of the impedance of a capacitor as the frequency goes to DC conditions, we see that that approaches 1 over 0, which equals infinity. In other words, the impedance of a capacitor in DC conditions is infinite. In other words, an open circuit. Likewise, inductors, we said, act like short circuit elements under DC conditions. So if we take the limit as we approach DC conditions of the impedance of an inductor, we see that that limit is 0. In other words, the impedance is under DC conditions is 0. Okay, so the first step, once again, is to transform the circuit into the frequency domain equivalent, and that involves 2 substeps: convert voltage and currents to phasors, and convert passive element quantities to impedances. The second step will be to take that frequency domain equivalent circuit and then solve for the current and the voltage phasors. We can use any technique we talked about so far. So KCL, KVL, voltage division, current division, etc. And we're going to talk about some additional techniques in the next module that will be even more useful. And the third and final step is to transform the solution of the voltage or current phasor that we solved for back into the time domain. So we do this by taking the real part of our phasor that we solved out, whether it be the voltage or the current. So taking the real part of the voltage phasor is like taking the real part of what we described as being phasor in exponential form of Vm e to the j theta, for example, which is going to be equal to Vm cosine omega t plus theta. And again, recalling that this is true because Vm e to the j theta is equivalent from Euler's identity to Vm cosine omega t plus theta plus j Vm sine omega t plus theta. So when we take the real part of that, we're just taking the cosine segment of that solution. Okay, let's do a couple examples. So in our first example, let's find the equivalent impedance from nodes A to B of this network. So at this point, you might want to pause the video and try to solve the problem yourself, and then you can restart it and look at the solution, or fast forward if you get it. We've got inductors, resistors, and capacitors in this problem. Note that I've already drawn the circuit in the frequency domain for you. You know this because everything is in the units of ohms, and you see the complex numbers also showing up, the imaginary numbers. Okay, so since everything's in units ohm, we can use the rules of resistor combinations to simplify this. So we know that this branch over here, our elements are in series. So the equivalent impedance of this segment, we'll call it Z1, is just equal to 30 plus J10. This capacitor and resistor are in series, so we can call that Z2, and that's just 20 minus J50. So from this point, we could simplify the circuit into the 25 ohm resistor, the J15 inductor, and Z1 and Z2. We note that Z1 and Z2 are in parallel with one another. And then once we have that parallel combination, we note that every element's in series with one another, so we can write the end expression of Zn as being series combination of the 25 ohm resistor, the inductor where the impedance is represented by J15, and the parallel combination of Z1 and Z2. And performing that math, we can simplify this into being equal to 51.1 plus J 9.9 ohms. Again, Z should be a complex number, and in this case it has a real component and an imaginary component. Note, because of this, we could actually simplify the circuit into an equivalent circuit that behaves the same way between nodes A and B with only two elements. So we could redraw that circuit as having two elements, a part that has a real component, which we know are only resistors, so that would be a value 51.1 ohms. And since we're summing them, it's another component in series. And so noting that that element is given as a positive imaginary number, we note that inductors are what result in a positive impedance. We can put that as a series inductor with impedance of J 9.9 ohms. So this circuit, starred here in red, behaves identically to the circuit that was in our original question. So continuing on with this example, we found an equivalent impedance. Let's say that we take that equivalent impedance and apply a voltage source given by the voltage phasor 15 at an angle of negative 45 degrees. Let's assume omega is 500 radians per second. So in the time domain, that voltage source would be Vt equals 15 cosine 500t minus 45 degrees volts. So assume we are going to drive that impedance combination with that sinusoid given in red. Let's solve for the current phasor and the time domain solution for I. So noting that we are just driving a single impedance, Z equivalent, we can find the current phasor I bar as being V bar over Zn given as Z equivalent given by Ohm's law. So that's 15 angle negative 45 degrees divided by 51.1 plus J 9.9. Note that we got the top, the numerator in polar form and the denominator in rectangular form, so we generally want to convert one of those to the other form to make that easier to compute, or even possible to compute. So doing so and simplifying, this simplifies to 0.16 minus J 0.24 amps. So that's the solution to the current phasor in rectangular form, converting to